Hello. In this video, we are going to be talking about trees, and we're going to be doing a couple examples of graphs, trees and parent codes, just so that you have a sort of reference for that before you work on the homework. All right, tree. A tree is a connected graph with no cycles. So that means that our graph has to be all one piece, right? We're not talking about graphs that look like, here's a graph and here's a graph, but really that's all one graph together. We don't want that. We want individual connected graphs. So here's 4 different graphs, and we want to determine whether or not these are trees. And the main property, besides being connected, is that there can be no cycles. So if you're a little bug walking around on this graph and you start walking around, there's a cycle if you can follow edges and never repeat an edge and end up back where you were. All right, so this first graph, right, this is not a tree because there's several cycles. Here's one. But this graph, right, this second one is a tree, right? No matter where you are, if you're walking along edges, you can never get back to where you were without backtracking. Here is another graph that is not a tree. The whole graph is just a cycle, a 2 cycle. Here is another tree. So this is one tree on 5 vertices, but you can have sort of any arrangement of the edges as long as you don't have cycles. So for instance, here's another tree with 5 vertices that looks different from the one before. All right. You should, on your homework, choose trees with 5 vertices that are different than those 2. Okay, let's talk a little bit about parent and child relationships. So for this, what we need to do is we're going to label our vertices, and our convention here is that we're going to start labeling at 0 and label 0, 1, all the way up through n, and 0 is going to be what we call the root. Okay, so I'm going to label 0, 1, 2, 3, 4, 5, 6, 7, 8. And if you want, you can sort of redraw your graph. You don't have to do this, but you can redraw so that your root is up here and everything else comes down from that root. So from the root, we've got vertices 1, 3, 4, and 5. So it would be like 1, 3, 4, 5. And then from vertex 1, we get vertex 2, and then from 5, we get 6 and 7, and then also, whoops, nope, that was a mistake. Let's go back and check. From 5, we get vertex 6, and then from 6, we get 7 and 8. So we can sort of see, right, how things get further and further from the root. So the root is sort of like the ultimate parent or ancestor, and then every layer you go down, right? So here's 1 away, here's 2 away, you're going to a child. So 1 is the child of 0, 2 is the child of 1, right? 3 and 4 are both children of 0, but they don't have any children. 5 is the child of 0, but 5 is the parent of 6. 6 is the parent of 7 and 8. Okay, so we can use this sort of structure to encode a tree. And it should be noted there's not just one way to do this, because we could have labeled our graph very differently, right? It would look different if we sort of switched our labels of 0 and 5 and had 5 here and 0 here. Things are going to look different. The code is going to look different, but you'll end up with the same graph. Okay, so let's go back to our original. There we go. All right, and we should note here that when we talk about closer and farther, I'm not talking about like, straight line distance with a ruler. I am talking about in terms of edges. So for instance, right, 7 is 1, 2, 3 edges away from 0. But 6 is only 1, 2 edges away. 6 is 2 away. So that means that 6 is closer and 7 is farther, right? Because you would have to walk from 0, you'd have to walk 1, only 2 edges to get to 6, but 3 edges to get over to vertex 7. Okay, so closer, farther is in terms of number of edges that you have to walk along to get there. All right, let's talk about the parent code. So this is for a tree with labeled vertices, and we're going to assume 0 is the root. So here is a tree with labeled vertices, labeled 0 through 8. So 0 here is our root. And the convention here is that we're going to encode this tree with 2 rows of numbers. And the first row is just going to be 1 through 8, right? The other vertices, every vertex except a 0. Okay, so that's taken care of here. And then the bottom row, you look at the number and you see what is that vertex's parent. So let's let's look here. Okay, so I'm going to start with 1. And I go and I see, okay, here's vertex 1, and I look, and its parent, right, I go from 1, I walk closer to the root. So from 1, if I go closer to the root, I get 0. Okay, and then 2, well, here's vertex 2, and I walk closer to the root, and I get to vertex 1. Okay, and then let's see, vertex 3. 3 is going to be similar. I'm at 3. I walk closer to the root, right? I'm walking along. I'm not talking about ruler distance. I'm talking about walking along edges. So I get 1. 4, I walk closer to the root and I get 0. 5, I walk closer to the root and I get 7. 6, I go closer to the root, its parent is also 7, so you can have numbers show up more than once. And then 8, I go closer, whoops, I skipped it. Okay, so 7, I walk closer, its parent is 0. 8, I walk closer, and its parent is 7. Okay, so here is the parent code. So we've taken this graph and encoded it with, right, these 2 rows of data. So it's like a 2 by 8 matrix with entries between 0 and 8. But our convention, right, our convention for the top row was that it was always just going to be 1, 2, 3, all the way up to the number of edges that we have, or the number of vertices that we have, sorry. So what we can do is, instead of taking, all of this, let's just take the bottom row. Since the top row is always going to be the same, we'll just take, let's make sure we copy it down correctly, 0, 1, 1, 0, 7, 7, 0, 7. Okay, so here's our father code for that. All right. Let's talk about, we'll come back to this example. Let's do another example where we get the father code, or the parent code, sorry. Okay, get the parent code. I'm just going to draw a tree. Okay. Yeah. Okay, and let's label our tree. Generally, you'll be given labeled trees. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and we start with 1. So from 1, you go closer to the root, and I just end up at the root. Okay, from 2, closer to the root gives me 1. From 3, closer to the root gives me 2. From 4, closer to the root along the graph gives me 3. From 5, closer to the root gives me 4. Here it changes a little. Now at 6, closer to the root gives me 7. From 7, closer to the root gives me 4. From 8, closer to the root gives me 7. And from 9, closer to the root gives me 8. So our parent code here is 0, 1, 2, 3, 4, 7, 4, 7, 8. Okay. So here is our parent code. All right. So we've seen 2 examples of going from graph to parent code, right? This string of data. And let's go from a code and talk about whether or not this represents a tree. Okay, so first of all, right, this is giving us the bottom row, and the assumption is always that the top row, let's do this in a color, the assumption is that the top row is always just starts at 1 and goes from there. Okay, so what this tells us, right, 1 through 9, is that we have 9 vertices plus the root, which is labeled 0. And I'm just going to kind of draw edge by edge, and we'll go along and sort of see what happens. Okay, so this tells me, right, that I have an edge between 1 and a 0. So I'm just going to draw, so here is my root 0, and that tells me I have an edge between 1 and 0. And then 2, this tells me I have an edge from 2 to 1. And remember that the bottom row is closer to the root. So I have an edge from 2 to 1, and 1 is closer to the root. This tells me I have an edge from 3 to 1, and 1 is closer to the root. This tells me I go from 4 to 3. Okay, now this one tells me I go from 5 to 4, and there's no one right way to draw this, right? So I could be drawing it, you know, looking like this, and that's still perfectly correct. Okay. Let's see, so we did from 5 to 4, and now we want to go from 6 to 7. Okay, and notice I don't have 6 or 7 anywhere on here, so I'm just going to draw that edge over here. And I know I go from 6 to 7, and 7 is the one that's closer, so I'm just going to draw it with 7 sort of closer over here. This one tells me I go from 7 into 8, so I'm going to actually move that back a little bit. Okay, so give myself a little more space. All right, so I go from 6 to 7, and then I go from 7 to 8. All right, and then the second to last entry tells me I'm going from 8 to 3, so there's how that gets connected up, 8 to 3, and then I go from 9 to 8. Okay. All right. And there is our tree. And like I said, that's not the only way that you could have drawn it, but we get that, yes, this does represent a tree, and here is that tree. Okay, let's do one more example kind of like that one. Okay. Okay. So does this code represent a tree? And we want to justify, right? Why or why not? Okay, so let's have 0, 1, 2, 0, 1, 2. Okay, so this would be a different number of vertices, right? So 1, 2, 3, 4, 5, 6. You line it up. This would be closer to the root. And let's try to draw this. Okay, so we're still always assuming 0 is the root. So this tells me I have an edge from 1 to 0. So 1 to 0. This tells me I have an edge from 2 to 1. Okay, 2 to 1. This tells me I have an edge from 3 to 2. This tells me I have one from 4 to 0. This tells me I have one from 5 to 1. This tells me I have one from 6 to 2. So yes, we did get that it is a tree. We didn't run into any problems there. Let's actually do one more where we look at this. So let's say, all right, so let's say 2, 4, 5, 2, 1, 5, 2. Okay, so again, we're going to line it up. And we're going to try to draw it. And let's actually say that this last one is 0 instead. Okay, so this first one tells me I have an edge from 1 to 2, and 2 is closer. This one tells me I have an edge from 2 to 4, and that 4 is closer to our root. This one tells me I have an edge from 3 to 5. This one tells me I have an edge from 4 to 1. And that is a problem because now I've created a cycle. Okay, so if there's a cycle in there, then we know that this is not going to be a tree. All right, if we went one further, we would see another issue as well. So 5 to 5, an edge from 5 to 5, right? That's a loop. That's another cycle. So we know it's not a tree. And then we've got an edge from 6 to 0. So there are several reasons this is not a tree, right? It's a cycle, so it's not a tree. It's also disconnected. So basically, you just go and you try to draw it in the same way, but if you run into something that is automatically not a tree, like a cycle or two separate pieces, then you know that it's not a tree and you can stop.